Hello everyone, welcome back to Let's Unbound. So we are in 2.6 of Unit 2, Competing Function Model Validation. Without any delay, let's get into the lesson. But yes, be ready with pen and paper and also your calculator. I'm gonna teach you with the help of Desmos today. So here, what is this competing function model validation? So whenever we come across a real life situation in mathematical modeling, we will like many things will come: linear, exponential, quadratic, polynomial modeling, and we will compare which will best the real world data, because real world data will be not perfectly aligned with one function. So we will decide and we will test which will be the best, and we have to validate it, right? So that is what the essence of this topic. Now, so we have already come across linear, quadratic, and exponential modeling. We will be focusing today. So when you're determining whether linear or exponential model is a better fit, you have to consider the following. Yes, linear means linear and exponential, their behavior is completely different, right? The pattern of change when you are dealing with table of values, graphing behavior, this will be very straight. This will be kind of growth, decay, and real world context. So we will check with like compound interest. These stuff will not suit linear, right? But simple interest will suit linear. Then data points, yes. When we deal with the table of values, like equally spaced x values, and then how the pattern changes, right, with data points and mathematical characteristics also. We will use sometimes to justify a model and to compare two different models here. Okay. Now, the key idea is use the contextual clues. Linear model means constant rate of change, right? It's a straight line trend. Quadratic, rate of change is not constant, but the way the rate is changing will be constant. And parabolic trend, like speeds up and then slows down steadily, or one peak point, right? Like that. Exponential model changes by a constant percentage or a factor over equal intervals of time, like rapid growth or a rapid decay. Now we should understand this residuals and residual plots. When we do exponential regression, linear regression, right, and when we justify model, validating a model, we need to aware about this. So what is residual? Residual is actual value minus predicted value. So there will be set of data points given to you. That is actual reality values. Predicted value is you will try to model a function. Maybe using this, okay, you see some data points are like this. Okay, let me model a exponential regression. So that exponential regression will not cover every point. So, but it will around take some points, right? So here, some points, your actual points are not within your regression curve. Some things within the curve, right? So this is where residual comes. So residual is the vertical distance. So here is my actual, this is my regression, like the best fit, and you have to find the vertical distance. That thing is your residual. Now, finding residual, and as a residual plot, we will collect all the residual distance and plot it over x-axis. If you got a positive residual means actual value is above the model. So the set of data points are actual, it's above the model. So these are positive. Negative means below the model. If something is below, it's exactly on your regression, means like model hit exactly the regression. Like the data points hit the model exactly. Okay. So this is residual concept, and coming to residual plots. Yes, this will help us to tell whether your model is good fit or not, and validating, justifying, whatever. So a residual plot is just a graph of all residuals. So we are finding that vertical distance, right? Uh, so those will be marked over a line. And we will observe how it looks like. The scattered plot is randomly scattered around zero. Zero means like y is zero. That is x-axis. The model is a good fit. But if your residuals are making any particular pattern, you can easily tell a shape of that scattered thing, means it's not the best choice. We should change the model. right? And then change the model, regression will change. Then you do the residual plot. Maybe that model will give you the good fit residual plot, right? And one more thing is residual error. Residual error is predicted minus actual. Predicted will be on your graph, like on your regression. Actual will be the data points provided, the reality values. So prediction is higher, positive residual. Prediction is lower, negative residual. Right, so that's it. Now here is an example. The green are data points and the regression is done. The red line is regression. So the green points are actual. The whichever on the red curve is the predicted values, right? And I have plotted like vertical distance from this to this. It's very minute value. So I will find all the vertical distance. It's exactly here. Now here, here. So and I plotted it over here. Okay. And I see it's randomly spotted above, below, something like this. So you can't predict a pattern here. So this is a good fit. We can go with the model. Right. So this is the thing. And now we are moving to first question. The number of subscribers to an online learning platform has been growing as a platform gains popularity. The table shows the number of subscribers in thousands after a certain number of years since launch. So years since launch in subscribers, find an exponential regression curve in this format. And here you can round your A and B to 3 decimal places. Use your model from part A to find the predicted number of subscribers at t equal to 2. Then find the error at t equal to 2. And then is predicted value an overestimate or underestimate? So we will see how to state overestimation and underestimation here. Right. So from the table of values to make a regression, we are going to use Desmos. Let me share that screen. Okay. First, you need to list down the points like table of values. You just give it here. Go for table. And like we have 0 to 5, 8, 10. The x values are, I mean the independent t there, but 0, 2, 5, 8, 10. So it's not equally spaced. Then subscribers is our y values, dependent variable. It's 50, 75, 150, 300, and 450. So let me adjust the window. It's not visible, right? So x, your minimum is 0 and maximum x is 10. So let me take 12. Y-axis minimum is 50. Okay, let's go from 0 to 500. Okay, and step maybe 50s. Okay, let's adjust the graph, something like this. So this is the data plot. And we need to find the regression, it's the first part. So for regression, you have to go something like this. Y1. Actually, they suggest you the regression. Even though they don't suggest, you will choose the data points are similar to exponential growth. So you will go with exponential. Okay. So y1 similar symbol a times b power x. So just go with exponential basic like general notation, but don't use yx. You use x y1 x1. Okay. So this is the thing. And also this will provide you the E1 plot, right? That will give you the residuals. Okay, it's a good fit actually because it's random scattered, no particular pattern here. Okay, right. So we don't want residual plot now. And store this equation whenever you make a regression. So let me store it as they have asked us to round it off to 3 decimal places. But for storing, I think you can take almost everything listed. Times your b is 1.2447 power x. Okay, so this is your function. This will help us to evaluate the future questions listed there. Okay, so let me answer the first part. Here to the whiteboard. So I have this. Using this, let me solve for A first. So don't write f of x. In the context is it's s of t. So s of t is rounded to three places. So 50.882 times 1.244 power t. This is your A part. We round it to three decimal places. Right. Now use your model from part A to find the predicted number of subscribers at t equal to 2. So this thing will give you the prediction. So for B, you need to find S of 2. Right. So you can just plug in 2 here in that. So we can find it. And also we need to find error at 2. Error at 2 is the predicted value minus actual value. Predicted value at 2 minus actual value at 2. Predicted means from graph, actual means actually what is given in your problem. Right, so we are going to do this in calculator real quick here. So f of 2, actually in our contest is x of 2, but here it's this. Now error also let's find. F of 2 minus actual value, you should refer to the table, it's here. Right, 75. So this is your error, 3.8. So that's it. We can answer the remaining B part here. So let's move to the whiteboard here. So your S of 2 is F of 2 in the context. So that is equal to 78.801. It's subscribers, right? And it's 10 subscribers, 1000 subscribers. The S was given in thousands. So into 1000, if you do, it will be 78,800 something. Okay. So when you list out, like when you write down, you can mention like when you explain the answer, when you present your answers, you can convert to thousands. An error to predicted value at 2, so we just did everything and it's 3.801 approximately. Okay, that's it. B part is done. And C, is the predicted value an overestimate or underestimate of the actual value? So this is your prediction curve. And every point, so it differs to every point. So it's an overestimate means your actual value is, okay, let's do, actually it's the predicted value at t equal to 2 is what they have meant. So if your actual value is above and your predicted is below, right? So your prediction is underestimating it, right? So let's see what happens at t equal to 2, right? So that is 78.801. This is predicted value. Actual value is 75 only. So it's overestimates. It's 3 more than that. So if your prediction is greater than actual, overestimates. Okay. So in this case, your graph will be above, your dot will be below. So prediction over above, right? So that is the C answer. It's overestimates. And with this, we are completing this problem and moving into question 2. The height of the ball thrown in the air can be modeled as a function of time t after it is thrown. The table shows the measured height of the ball at different times. Again, it's given, it's very, very similar to what we have done in question number 1, but quadratic regression, that's it. So you can pause the video and try the problem on your own. So it's time for pause. And you can check the answers with me after some time, right? So pause the video. And here is how we will solve. Okay, again, we should make a regression, quadratic regression, round to 3 decimal places, find the error, overestimate or underestimate, right? So we are going for calculator directly, all the process same. Only we should take care of quadratic regression. We should go with standard form of quadratic. So go for tables. It is given 0.5, 1.5, 2.5, 3.5, kind of that. So it starts with 0.5, 1.5, 2.5, 3.5, 4.5. And we can give the values 640, 17, 15, 9. And we are going for quadratic regression. Let's adjust the window here to have a better view. So x is 0. Let's go for 0, 2, maximum it's 5. So it takes 8. And your y-axis is 0, 2, maximum is 70. So let's go for 20 or 45. Steps is not 50. So it's not mentioned. That's it. So this is your curve, and it's clearly says it's a quadratic regression. You can suggest that model. So yeah, how will you name? Y1 is similar to a x1 squared. So we first square it and then give the suffix x1. And you have to give full thing. Don't bx1 plus c. So we will get all the parameters, regression parameters here. And it's almost, I think this is the greatest fit. Yes. So this is what we got here. And you store the equation as f of x. Again, that will be helpful. So what is your a? Negative 2.35. So copy that, x square plus b is 12.4. This thing, copy paste, and x plus c value 0.432. Okay, that's it. Yeah. So now going back, we did this. We have to approximate to 2 decimal places, right? So let's use this and make the regression model. Moving to the whiteboard here. Okay, so that's it. First part is regression model. F of x, okay, h of t actually, with the context. H of t is negative 2.357 x square plus 12.486x plus 0.432. This is our regression, quadratic regression. And we have to do, yeah, that's it. Use your model from part A to find the error. So how will you find error? Error at 3.5 is your predicted value at 3.5 minus actual value at 3.5. Okay. Predicted value, you can substitute here or you can use graph there. Better use graph. And actual value is from the table of values or from your description, problem description. Right. So here I'm going to find error. So error at 3.5 is f of 3.5, that is your prediction value, minus 3.5 actual value is 50. This is your error, 0.257, something like this. Okay, that's the thing, and we are moving to whiteboard back. So for B, this is our answer. So it's 0.257163, something like this. This is the error. And is the value predicted an overestimate or an underestimate of the actual value? So yeah, if your error is positive, it's an overestimate. Okay. So, and also you can check it in the graph, but here it's very closely given. So f of 3.5, it's 15.25. Your prediction is greater. But we can see that it seems like very closer at 3.5. It's your actual value is at 3.5, right? So here is 3.5. Your actual value is little below. The graph prediction is above. Prediction above. So it's an overestimate prediction. Okay, and that's it. We are completing this problem C. It overestimates at 3.5. Okay, we should do at every point. So it's overestimates at t equal to 3.5. And that's the case. Now, moving to third problem. It's very simple but effective one. Miss Lee owns a food truck and tracks her daily revenue over several weeks. She used an exponential regression model to predict her revenue based on the number of weeks. Based on the number of weeks since she started her business. The figure below shows a residual plot. Which of the following options about the exponential regression is true? Okay, first let's see. Residual plot with your model, like you are going to validate this. Is it a random scattered? No, it's not randomly scattered. Correct. So I can see a very clear pattern of residuals, right? So if you see a clear pattern, it's not a good fit. So it's not a good fit. And but not a good fit, not appropriate. Two options are there, C and D. Because there is a clear pattern in the residuals, and here residuals are not random numbers. Okay, we will stick with the word, okay, something random. Randomly scattered random numbers. This doesn't make any sense. Randomly scattered, we are not talking about random numbers. So C is the apt one. There is a clear pattern. Okay, don't fall for the word random. Random numbers doesn't make sense here in residual plot. Randomly scattered, something like that is accepted. So it's option C. And that's the wrap for, yeah, of course, there's a bonus question. So a town's population over time is given as a table of values. Determine whether a linear or exponential model best describes. Write an equation for best fit model used to predict population after 5 years. And then determine when the population will exceed 10,000. We can round it to decimal place if it's decimal years. Find average rate of change and interpret the meaning of base B in your exponential in the context of the problem. So it will help you in a wholesome review. So do solve the problem on your own. If you have any doubts, you can post that in comment section. So we would like to help you here. And that's it. If you want to join Let's Unbound student community, you can scan the QR code given here. I will be meeting you in next video very soon. Until then, keep learning, keep practicing, stay curious.